Hello everyone, I'm Yves Delabroise, software architect for Kingstar at Interval Zero, and I welcome you to this short video on modular machine building. So we prepared this video and a webinar on it to explain the concepts and technical requirements on modular machines. Nowadays, everybody is asking for machines to be modular. The main reason for it is, well, as usual, money. Having a modular machine means that you can have a single controller and single hardware and software base for multiple applications, for multiple machines, which reduce the costs of maintaining multiple sets. And the second one is that this way you can address new markets and update machines faster, because as components are all modularized, you only need to update or add new modules instead of rebuilding a complete machines. So the first topic is, when we're talking about modularity, what are the different types of modularity we're talking about? The first one is what we call a pluggable unit. A pluggable unit is in itself a machine, but that is rarely used standalone. It is connected to another main machine and it helps it. For example, it can be a loader-unloader system, or it can be a testing or an inspection system that you add on a machine. The second thing we often see are optional hardware. Optional hardware is when you have a machine that processes a part, creates a part in PCB, and then you will have options to it, such as engraving, flipping a board, testing a part, or things like that. The next very common type of modularity is versions of the hardware used by the machine. You can perform the same task, no matter whether it's milling, testing, or things like that, but with different size and precision levels for parts which are larger or which are higher end or lower end. So for this, you will have the same tasks and therefore usually very, very similar or identical applications, but the hardware itself will be different because it needs to be bigger or more precise or things like that. Once we've seen the modularity in hardware, we're now going for the software. So same thing for softwares, you will have optional modules, which could be tools, analysis, result presentation, connection to other systems. And one of these software modules will be the machine interface. Now, a machine is not a standalone, it works in a factory. It has to be connected to other equipments in the factory, such as machines, SCADA systems, MES systems. And this is done through, nowadays, protocols instead of IOs. And every factory decides its own protocol. So the machine builder will have to support many different protocols for it. The last type of modularity is task modularity. No matter the type of machine, whether it is testing, packaging, milling machines, they will need to perform different tasks on different pieces. Therefore, you need to have a module that specifies the task to use on the current piece. To achieve these modularity, to allow these modularity, there are some architecture requirements for the machines. So we'll now present those requirements. The first one is when you're building a hardware or a hardware module, you have to decide how you want to build it. Instead of it being a complete machine, which has its own controller, front end, and everything, it could be a hardware cell, which is a hardware module plugged into a machine. This means it has no controller at all. It only directly connects to a field bus inside the machine, and the main controller of the machine will connect and control it directly. So this is, for example, let's say in PCB to flip a board. If you need to flip the board, it could be in packaging, a module to do some labeling, to do some pushing, to do some sorting. So this doesn't need a controller. It uses the main controller of the machine. But in some cases, like for example a robotic arm, it will this may work with machines of different vendors. This way, it's more complex and it needs to have its own controller for safety, because a main controller may often know how to move an axis or how to control I/Os, but doing a more complex system, it may not be its specificity. This way, the module itself, the hardware module itself, will have its own controller. But to be able to cooperate with a main machine, it will need to support a slave mode in its controller. This means that instead of having an application in the robotic arm and the slave controller receives commands from the main machine. Therefore, there is no application inside the robots or the other slave controller, and the application from the main machine will send commands to the slave controller, which will move. It will use its own logic to move, but it will have the application done remotely. The next very important component is to have a hardware abstraction layer. This is because you will have multiple types of hardware. For example, when you want different size, different precision levels, or even when you will renew hardware because hardware will evolve, and for the next version of your machine, you will need to use newer versions of the hardware in it. You need to be able to abstract this from your application to avoid having to rewrite the complete application for every time a hardware changes. The next step is having a modular software. This goes, for example, one of the modules will be the hardware abstraction layer. That layer handles the hardware, and when it changes, the rest of the application doesn't need to change. But this is also true for other modules, such as the interface to other machines or application for special hardware cells that you will add. This way you can have multiple applications or multiple libraries working on one single controller to control the machine depending on what components are plugged in it. The next step is one of the modules, which will be the machine interface. This one has to be independent and has to support many different protocols. As we said, when you sell a machine, it goes into a factory. This factory has an existing network with an existing protocol, which may be very recent or older. The machine has to be able to interface with the existing hardware and with the existing factory. Therefore, a module which may be hardware or software or both will need to be implemented for the controller itself, the logic, to be able to pass the data no matter the format of the factory. The last architecture requirement is the task files. Tasks need to be easily loaded, unloaded, and modified by the operator. Therefore, a simple file is the most suited solution, as it can be easily copied and exchanged with servers. The most common example is GM code, where a simple text file has commands describing how the axis will move and what has to be done on the piece. In order to achieve these architecture, there are some technical requirements that will come into the machine and into the way it's done. The first one is going to be a field bus inside your machine to connect to the different hardware cells and to the different hardware I/Os drives. You will need to have a field bus with hot connect, bus scan, and automatic configuration. Why is this? Because if you have no field bus but you are using boards to connect, well, you have to have more or less boards depending on the modules. You have to have a specific board for each module, which makes things much more limited and much more complex. With a field bus, you can add hardware without modifying the controller, the PC on the controller. It needs to have a scan and automatic configuration because you will have optional hardware, cells, and possible pluggable units. These needs to be detected by the controller, and the correct applications must be loaded automatically based on what hardware is detected. And for larger machines, you may want to add, remove, or maintain one of the hardware cells while the machine is still moving. This is very important for slow processing machines because you don't want to stop the machine in the middle of a process. In that case, you need to be able to have hot connect to remove a hardware, maintain, modify it, and put it back on the machine without the system closing being stopped. The next step is that, well, you need to have a standard PC, because to be modular, you will want to have optional components, optional software. Therefore, depending on the machine, you will have a low-end or a higher-end controller. And if this controller has an ARM or a very specific board kind of architecture, it is very hard to scale. Standard PC is the only way to be very, very scalable. When you have many pieces of a single controller, it is cheaper and more efficient to have a dedicated board or a dedicated ARM PC, because this is built for your need and it is cheaper. But when you want to do a modular machine, it means you will have many different variations of your controller, many different variations of this PC, which means for each variation the volume drops dramatically. And in this case, it is much more expensive in time and in price to build and have these PCs, these dedicated boards and dedicated ARM PCs built for your application, for your system. You have to select them, order them, when it's only worth it when there's enough volume. So when you do modular, you will have many different variations for one single application. So a standard PC becomes the simplest solution, what you save in time and usually in cost too. The next step is that to be able to have a modular software, you will need to have a subsystem. Well, the subsystem is going to be like the kernel of your controller. It will connect to the hardware abstraction layer and present the hardware abstraction layer to different modules of the machine to be able to load those modules, and it will also allow the modules to talk to each other, to discover each other and talk to each other. Some of the main modules you will have are going to be the machine, the hardware abstraction layer connected to the field bus. Then you will have the machine interface for machine to factory communication. You will have a human interface, which will usually be the main controller, the main interface to select, to stop the machine and to do operations. All of these, some need real time, some do not. They need to communicate and to be loaded depending on the hardware. So the subsystem component is like the software platform that will allow all these pieces to interact. The next step is going to be standard communication and control. You will want, even now with all the hardware issues, finding hardware, selecting hardware updates, software updates and evolutions, you will want to have backups for everything, both software and hardware, because if one of your vendors disappears or cannot sell you at this point, you will want to be able to switch. This is why everything has to be based on standard. Standard PC x86 allows you for multiple vendors. Standard field bus allows you for multiple drives and I/O vendors. And then you will want to program with standard languages such as C++, PLC language, maybe .NET, maybe Java, which will allow you to switch to another control. And the APIs and interface for the control need to also follow the standard. For example, the CAN-open DS402 communications with drives, the PLC open motion control standard to control access and I/Os. The next step is that you will need a scripted task. This is for the task file. It needs to be text because it needs to be easily modified, uploaded, downloaded, human readable to see what's the next step. So this scripting task file is what will allow you to modify the task of your machine, synchronize it potentially with the cloud for the batches of one machines, where for each piece you will switch the file. It can be done automatically by loading a file based on a barcode value or something like that. And the last piece is remote control and maintenance. It used to be too expensive, and now it is even harder to go on site to your customers and send somebody who is very knowledgeable of the machine, is able to go do diagnosis, find the issue on a machine that is not running at your customer's site and fix it. The new standards now is to connect remotely to this machine, do a diagnostics from an engineer which is in your head office. They can find the problem, know how to modify it, and build an SOP that is sent to a local operator, partner, or distributor who will follow the SOP to fix the problem or replace the piece that needs to be replaced. The next step is presenting our Kingstar product and how it fulfills and helps our customer make modular machines more easily. First, Kingstar is a PC-based real-time control platform, which includes real-time OS, field bus, motion, PLC, vision, and IoT products. The field bus that we have selected for this platform is ESACAT, and we built an automatic configuration on top of this ESACAT master. ESACAT is selected because it is the field bus with the most users, the most choice in terms of drives and IOs. And it supports updates of the hardware over the network, diagnosis of the hardware over the network, scanning of the connected hardware, identification, hot connects of the hardware, and branches. So it allows everything that you need to have a very flexible and self-diagnosis on the machine for remote maintenance and local maintenance. Then we are fully standard-based, which means for the field bus, we use ESACAT. To connect with the drives that are connected to ESACAT, we follow the CANopen DS402 communication. Then, for the communication on how the user application interacts with our motion control, it is following the PLC Open motion control standard in terms of how the moves are done. And then for the communication with the cloud or with the machine, we also provide OPC UA, which is the newest standard for communication from machine to cloud, machine to HMI, and SCADA. Thank you for listening to this video and watching this video. If you want to have more information, we have a white paper with more details on this on our website.